Dear students, we like to discuss the early age shrinkage because it results in cracking. There are different types of shrinkages which you have already learnt in another subject, but for the sake of information again, the main types of plastic shrinkage, chemical shrinkage, autogenous shrinkage, and drying shrinkage. We can discuss these mechanisms. Some of these mechanisms are overlapping, and it may be difficult to find the governing mechanism. However, after seeing the shrinkage curve, you should be able to identify different mechanisms. Actually, shrinkage is consumption of capillary water, and capillary water is held into two uh, categories of capillaries. Number one category is large voids of capillaries which are of size more than 50 nanometers or 0.05 microns, and this may be called free water because its removal does not cause any volume change. The second type of capillaries are the water held in small capillaries which have a size of 5 to 15 nanometers, the removal of which may cause shrinkage of the cementitious system. Now the water can be held in these capillaries as different uh, types. Number one type A is adsorbed water. This is the water that is close to the solid surface, and the loss of adsorbed water is responsible for shrinkage of hydrated cement paste. The other type of water which is held in capillaries is called interlayer water. This is the water associated with CSH structure. The interlayer water is lost only on strong drying, that is below 11% of relative humidity. The CSH structure shrinks considerably when the interlayer water is lost. The third category C is chemically combined water. This is the water that is an integral part of the microstructure of various cement hydration products This water is not lost on drying. It is evolved when hydrates decompose on heating. Now, plastic shrinkage cracking occurs when the concrete has not yet set. And you can see if in figure 20 the pattern of plastic shrinkage cracking. This occurs when the water evaporates from the surface of freshly placed concrete faster than it is replaced by bleed water. The surface concrete shrinks due to restraint provided by concrete below the drying surface layer. Tensile stress is developed in the weak stiffening paste plastic concrete, resulting in shallow cracks. You can see figure 20. These cracks are often fairly wide at the surface. Plastic shrinkage cracks can be prevented by taking measures to prevent rapid water loss from the concrete surface. Fog nozzles, plastic sheeting, windbreaks, and sunshades can all be used to prevent excessive evaporation. Drying shrinkage cracking. Because almost all concrete is mixed uh, with more water than is needed to hydrate the cement, much of the remaining water evaporates, causing concrete to shrink. The restraint to shrinkage provided by the subgrade reinforcement or other part of the structure causes tensile stresses to develop in the hardened concrete. Restraint to drying shrinkage is the most common cause of concrete cracking, which you can see in figure 21. In many applications, drying shrinkage cracking is inevitable. Therefore, control joints are placed in concrete to predetermine the location of drying shrinkage cracks. Drying shrinkage can be limited by keeping the water content of concrete as low as possible and maximizing the coarse aggregate content. See figure 21. Now we will discuss early age shrinkage of self-compacting mortars, which are very common these days in different types of structures. Because mortars also contains aggregates, though fine aggregates, and you should expect that self-compacting concrete will be having shrinkage, early shrinkage lesser than self-compacting mortars due to inclusion of coarse aggregates. Now the contents of this lecture are the introduction, then the methods and materials used, then the apparatus used because there are different types of techniques to measure the shrinkage, results, and then conclusions. We can discuss further in the during the class. Introduction, many types. Total early shrinkage is very important because the designers or civil engineers need the total shrinkage, not the contribution arising out of different mechanisms which may operate parallel. And the codes of practice also specify the total shrinkage, not the different components of shrinkage. Shrinkage can be measured in volumetric measurements, linear measurements, and digital image. The one I am showing you is linear measurement, although in the protocols which we have discussed in the previous course, there is a relationship between linear and volumetric shrinkages. The materials which were used were SEM1 for 2.5R, SEM2 A-AA, which is containing limestone powder, 32.5R, and SEM3B, it is blast furnace slag, having 30% slag content. Limestone powder had 92.3% calcium carbonate. Fly ash for the ASTM class F. Rhesus caches, amorphous and crystalline both were incorporated. Silica fume, rhesus cache amorphous and RHAP is crystalline and silica fume. They were used 20% of the fly ash mass. Mix was 1-1-2. One is cements, number two is same amount of secondary raw material, and two is the sand. Water cement ratio is 0.4, and from this water powder ratio becomes 0.2 for all high performance self compacting mortars.